Now we would like to begin Dr. Stefan W. Hell's lecture. Today, Dr. Hell will be lecturing online. Dr. Katsumasa Fujita from Osaka University will be the moderator of this session. Please welcome Dr. Fujita.
Okay. Thank you very much. I'm very honored to chair this wonderful session from Professor Stefan Hell for this HOPE meeting. And since I started my career research, I'm being interested in optical imaging and developing optical microscope. And really early time in my career, I was interested in to go beyond the optical microscope of at that time level. And luckily, I had the same challenge that Professor Stefan Hell had at the time. So that is the super resolution imaging. So go beyond the limit of optical microscope. And at that time, I remember there's not so many groups working on that in the world. So I was lucky again because I had many chances to talk with Stefan in the conferences, and I learned a lot from his research and exchange ideas. So I also had a chance to stay his lab for a couple of months and learn more about his science and his very strategic way of research. So when I heard the news of Nobel Prize, I was so happy. So it is a very wonderful moment, brilliant moment for me in my career. And also at the same time, I was so surprised because the Nobel Prize chemistry was given to development of fluorescence microscope. So we are in optics and photonics field. So we wondered why, but eventually we understand our research field is quite interdisciplinary. So I think in his lecture, you can learn how it is important to work in this interdisciplinary field and together with his passion and energy to have made the impossible possible. Let's welcome Professor Stefan Hell. Okay, Stefan, so please start your lecture.
Thank you. Thank you, Katsumasa, for introducing me so wonderfully and personally. I would like to say hello to everyone, and I'm going to speak about actually my favorite subject, which was overcoming a scientific barrier, perceived scientific barrier, which was the resolution limit in light microscopy. And then I will show you that if you overcome a barrier in science, you also can make something out of it. And so this is actually a talk about how I came about doing what I did and the consequences of it. Now, you are probably aware of the fact that the resolution of a light microscope is fundamentally limited by diffraction. And this is actually, this view graph actually shows you that with a human eye, of course, you can see only down to about 1/10 of a millimeter. And the advent of the light microscope in the 18th, 17th century actually was able to show that by seeing small things, you can discover a new world. With the light microscope, cells were discovered, bacteria were discovered, and cellular organelles such as mitochondria were seen for the first time. However, you also learn in school, I'm sure about that the resolution, the capability of a microscope to see small things is fundamentally limited to about half the wavelengths of light if it's a light microscope. And so if you want to get a higher spatial resolution than a light microscope, you have to use an electron microscope. As a matter of fact, because of that, in the middle of the 20th century, the electron microscope was invented, and as a result, a much higher spatial resolution was achieved. And then viruses were discovered, even small molecules could be seen with electron microscopy. And the present day's electron microscopes are so good that they can basically see atomic levels or even subatomic levels. So very, very high spatial resolution. Now I'm going to talk about light microscopy. And the question is now, why would I care, being a physicist, as Katsumasa just mentioned, why would I care for a light microscope now that we have the electron microscope, and the electron microscope has a much better resolution? The reason is very simple. With an electron microscope, you can see only dead things. It's not possible to see living things with an electron microscope because you have to take out the air, you have to take out water, so you cannot see hydrated things in action, so to speak. And if you want to look into a living cell, you have no alternative to using focused visible light, so to use a light microscope. And there's another reason why light microscopy is so important. At present, we know already that a cell contains a nucleus and it contains organelles and so on. So that is already known. But what is not so much known is how certain proteins are distributed in a cell and how do they interact with each other. So what's going on in a cell? So functionality is something that we would like to understand. For example, if you want to know how a disease actually develops. And therefore, it made a lot of sense to readdress the resolution issue from a physics viewpoint and to ask, is there really no way to overcome the diffraction barrier of 200 nanometers and get a light microscope that can see smaller details than what people have thought that it would be possible? Now, this scheme that I'm showing you here, this sketch, I've been showing actually for, Katsumasa will remember, for 25, 30 years, since the time Katsumasa and I got introduced to each other back in Japan in the mid-90s. So why did I not change the slide? It's very simple. The reason why I'm using this slide is just as, excuse to tell people why it makes sense to look into resolution issue of light microscopy. My real motivation, however, was different. I wanted to know if it's possible physically to overcome this barrier. So from the physics viewpoint, is there a way to do it? I was not so much interested in helping biology or doing something for the life sciences. I just want to know whether it works or not. Now, what was the problem? Why did people believe that there is no way to get a better resolution with the light microscope? Now, physics can be very simple. And in this case, the resolution problem is very easily explained. The most important element of a microscope, light microscope, is the lens. And the role of the lens is to focus the light down to a point. Now, nowadays, people don't use lamps anymore as they used 100 years back. They use lasers. And of course, the laser is bouncing off this mirror and then is focused by the lens into the sample. Now, imagine that these little dots, the black dots, are molecules, individual molecules. And now the idea is that the lens focuses the light just on a tiny molecule or tiny feature. Now, that is not possible. Why is that not possible? It's not possible because light propagates, behaves like a wave. And if you focus a wave, you will never, ever focus the light down to a point. What will happen, you will get a blob of light that has a finite extent. And this finite extent is rather large. It'll cover many, many, many molecules, many of those features, because it will be roughly of the order of about 200 nanometers in this direction, and even about 1,000 nanometers in this direction. So many of these molecules will be illuminated at the same time. So many will see that green light at the same time. And as a result, of course, many of those molecules will scatter light back. Okay, so they will shine light, say it could be fluorescence light, and then it's a different wavelength, but it doesn't matter. It could also be reflected light. It's the same thing in the end. All of these molecules will emit light back. And then, as you can imagine, the lens will collect that light. It will go this way, and here it will pass this mirror, and here there's a detector. And if you put this detector in here, of course, it's very clear that also the light that comes from the molecules is diffracted. It behaves like a wave. So it also produces a blob in here. And then if you put a detector over here and watch what's going to happen, you will see that there is a big mess, because you see there is a many of these molecules here, and each of them makes this blob. And if you have many of them, there will be a big overlap of the signal. And if you put a detector, as I said in here, the detector will not be able to tell the signal from these molecules apart. It could be any of those, yeah? Could have been this molecule emitting or that one. As a result, it's not possible to separate these molecules from each other. No way to do that, because here there's a big mess and you don't know where the signal is coming from. Now, you could also put the eye, it doesn't matter. And if you take the fanciest camera that is produced by a very, 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 say, advanced company, many of them are in Japan, of course, doesn't help, because in the end, there's a big mess in here. So the person who realized this problem was this man. His name is Ernst Abbe. He lived at the end of the 19th century in Germany, and he kind of coined this equation, which is named after him. It's basically saying that the width of this spot, I'm paraphrasing it a bit, the width of this spot is given by roughly the wavelengths divided by this number. This number is something like 1.5 or 2. And so and with the wavelengths of light being about 600 nanometers, you easily end up, or 500 nanometers, you end up with 200 nanometers. So this is actually the best resolution that you get in the microscope. If you want to see details that are closer to that, then there you have to take electron microscopy. You cannot see details that are smaller than 200 nanometers. Now, Ernst Abbe was actually an entrepreneur and a physicist at the same time. And there's many reasons to actually make memorials in his honor, where he lived and worked in Jena in Germany. But this memorial is very special because it's erected in front of the physiology department of the University of Jena in Germany. And there on this memorial, this equation is written in stone, literally. And you can see now that this is what people believed. You cannot get beyond this limit. There is no way to get a higher spatial resolution. And so when I was a student in the late 80s in Heidelberg, in Germany, in physics, what I was confronted with, and I was asked to look into microscopy, laser scanning microscopy, this was the best resolution that you could get at that time. There was no way to get a higher spatial resolution. And people believed this is the end. So not only it was textbook knowledge, you can find this equation in any textbook, it also was a fact. Now, as Katsubasa certainly knows and has witnessed, the development of stat microscopy, which I'm responsible for, that came actually in the late 90s and then a couple of years later, actually showed that you can overcome this diffraction barrier. And there is physics, viable physics, that allows you to get sharper pictures, as you can see here. So this is previously, and now this is much clearer than what you've seen before. And so this microscopy, or called stat microscopy, showed for the first time there is a way to overcome the diffraction barrier, and it opened the eyes of the world to the viability to get much higher spatial resolution. And so it had a number of consequences. And one of the consequences it had for me was that in 2014, that's about 10 years back, close to 10 years back, I had the privilege of getting introduced to Northern European Scandinavian kings. And the first king I was introduced to was Harald V of Norway, because I had the honor of sharing the so-called Kavli Prize with two colleagues from France and from Britain. And so I was very proud of that. And that was in September 2014. And a couple of weeks later, I was actually called by a person on the phone, and the person kind of said, okay, now you will also have the privilege of getting to know Harald V's cousin, King Gustav of Sweden, because you will be invited to receive the Nobel Prize in Chemistry. And that's what happened on 10th of December 2014, where I was handed over a medal. This is, of course, followed by a very nice banquet, I must say. So whenever you have the chance of getting there, or maybe you win a Nobel, you can be very happy, because the banquet is really nice. It comes with very good food, and with very nice company. And so this is actually something that I could talk about now for half an hour. What can be seen and enjoyed at this very nice banquet. But I am not going to speak about the gossip. I'm going to come back to the science and how I got actually to the science. And since this is a motivational talk, I would like to share with you that, of course, always keep in mind that science is done by humans. And of course, I'm a human. I have to live a life, and of course, I lived my life in a specific way. And then in the end, I was also a scientist. And so I'm going to talk about my personal trajectory in life. Now, this is the map of Europe, as you may recognize. I was born in a western part of Romania. So this is Romania. This is Romania. This is Hungary, and born in 1962. And the funny thing is, I'm not actually born in the city. I'm from a small village with about 7,000-8,000 inhabitants. So it's very, very small by Japanese standards. Now, I was German ethnic, so my mother tongue actually is not Romanian. It is German. Romanian I learned in school, but my school education was in German, because Romania had for ethnic minorities schools in their minority language, and I had very good education, especially in physics. And I went to this high school, which now claims, as a matter of fact, 2 Nobel laureates. And the second one, actually, and she actually got it before me. She won, this woman, Herta Müller, she won the Nobel in literature in 2009. And the other funny thing is, if you think about that part of the world, not far away, just 50 kilometers from where I was born, actually stems Katalin Karikó, who just got the Medicine Physiology Prize this year. So I don't think it's in the water. Don't believe that nonsense. I think the most important factor for students and for the trajectory in life are teachers. And so I had the fortune of having very good teachers. But I would like to mention at this point that this was, of course, during the Iron Curtain, and so the 70s or so. And I convinced my parents to try to get out of communist Romania and move to a Western country, namely to West Germany. At that time, Europe was still divided. The Iron Curtain was still there. And so after many problems, we managed to move to West Germany, to a city called Ludwigshafen. It's actually famous for a big company called BASF. But anyway, we didn't go there because of the company. I wanted to be there also because it was close to Heidelberg, where I wanted to study physics. And so in 1981, I enrolled in physics and started physics in Heidelberg. And like most physics students, at least at that time, I was interested in theoretical physics. I wanted to do something profound, to maybe invent new kind of things and come up with new theories in basic physics. But at the time, I had to make a choice for what to really study in my PhD thesis. I asked other students, so what would they recommend to do? And they said, don't do theoretical physics. If you do theoretical physics, you will end up unemployed. You don't get a job because this is useless. There are so many theoretical physicists and there's no jobs, and you will never, ever become a professor. Forget that. Do something that is more applied and something where you can get a job in industry with. And this is why I signed up actually with a professor who had founded at that time a company. A company that produced laser scanning microscopes and confocal laser scanning microscopes. And so I felt that if I'm doing a thesis with him, then I'm doing something useful, something practical that would get me a job in industry. And what I was asked to build laser scanning to use laser scanning microscopes to inspect computer chips. So basically, I got computer chips from IBM, from Siemens, from Hitachi, and I was asked to really look into the line width, so the size of the say small spacings that are on the computer chips with microscopy, laser microscopy. And you can imagine this was totally boring physics because there's no real physics in it. And this is nothing. I mean, if this is just looking or taking pictures and measuring small distances. Yeah. So there was no real physics in it. And I was totally frustrated. I was close to giving up everything. I felt this is useless. Why I'm wasting actually my life and my career. Why would I do this? That's not what I studied physics and went through all the difficult parts of the subject, theoretical physics, and also other, say, hard experimental physics. This is the physics of the 19th century. Optics, there's nothing to be discovered anymore. That's boring. And so I was just about to drop out of my thesis. I was secretly shopping around for other PhD topics. Even 1 year after I started, I was so frustrated. I could hardly expect the weekend to come. And on Monday morning, when I went to my PhD thesis work, I was frustrated. Anyway, and then I thought about it. Yeah, either I could give it up, or maybe I can do something with this boring subject. Maybe there's still something interesting to be done. And guess what? I felt maybe the only cool problem that is left over, yeah, in microscopy is to overcome this diffraction barrier, to overcome the resolution barrier, because everyone believes it's not possible to go beyond the 200 nanometers. And so if I came up with something, that would be really cool. And so that kept my spirits up. And so I decided to move on and to look into the problem, whether there is really a way to overcome this barrier. And it was very crazy thought at that time. So why did I believe that there might be a way? It's very simple. I said, okay, this barrier was found at the end of the 19th century, 1873 to be precise. But at that time, it was already 1989. So many years have passed. So much physics was invented in the interim. So in the time in between, yeah. So in this 100 years. So molecules were found. Of course, lasers were developed, spectroscopy, there was molecular states and all this stuff, quantum optics. So there must be something. There must be something that can be used, can be harnessed to overcome the diffraction barrier. People just didn't look at it because they're used to the fact that light microscopy doesn't get better and then just stop. And so I felt that if I look into this, I may have an idea that really gets me beyond the barrier. And so I wanted to convince my thesis advisor at the University of Heidelberg that we should look into this, but he said, no, I'm not interested. Actually, the company went bankrupt and was split up. I felt I shouldn't. He felt that he shouldn't continue with that. And so I went to EMBL first. That's a European lab, but it was not great there. But I had a very fortunate encounter. There was in Heidelberg, there was a Finnish colleague. He said, why don't you come to Finland, to a place called Turku that I never heard of before? I know somebody who has become a professor there, and maybe you can work in his lab, and maybe you can find some time, and then eventually you may have an idea, and then you may be able to do your work in science and even come back to Germany with a good idea. And that's why I went to Finland, actually, very reluctantly, I must admit, because I had to leave behind everything. And I was just a postdoc there on a stipend. But a couple of weeks after I got there, I had the decisive idea that eventually won me a Nobel Prize. And I'm explaining to you now what it was. Now, as I said, the role of the lens is to focus the light down to a point. But because light cannot do that, there will be a blob of light that has a finite extent. And because of that, there will be a big mess in here, okay, a big mess. And so that is clear. I accepted that. But what I realized on a Saturday morning, actually, in 1993, is that not only you can use light to make the molecules glow and produce light in here, you can also use light to turn them off. And so I realized, okay, why don't I turn them off, or at least some of them, and leave only those that I want to see? And so I realized that by taking a light of a different wavelength, like red light, I can make molecules turn off. And of course, I don't want to turn off all of them. Let's assume I'm turning off those here, but leave that one on. And then, of course, it's very clear that if I'm turning this one off, I would get signal only from this one. And then this mess that you see here on the detector will be gone because there's only signal from this molecule. And then I have basically what I wanted because I want to get signal only from this one. The whole system behaves as though I would have illuminated just that one. And this was a really profound idea because it meant by turning off and keeping those molecules off, of course, you can separate molecules. And so you see this one, and then you get signal from this one, and then how do you get the other one? How do you make a picture? You move on to the next, and then you move on to the next, and you register this and you put on display, like in the old CRT tube, and then you have a picture. And so this was a basic idea, and I called it STAT because the phenomenon to turn off is called in physics stimulated emission. And I published this as a theoretical paper. So Dr. Fujita will certainly remember that paper. And then I thought, okay, now with that theoretical paper, it was not experimental, it was not proven. It was just a theory, a proposal that it would work like that, a concept. I thought that, okay, I would get a job and I would be able to check out if it works or not. By job, I don't mean the professorship. I just meant a job as a scientist in a lab to try it out. The problem was that hardly anyone believed in this idea. So I went around. I went to meetings in America. I went to meetings in Europe. Actually, I would say it's fair to say that the first person who took it seriously was actually the lab where Dr. Fujita is from, Professor Satoshi Kawata in Japan. He invited me to Osaka, and he invited me, and he also came to, he sent somebody to Finland at that time to discuss this with me. So, but hardly anyone really believed that this would work. And so I couldn't find a job for 4 or 5 years. I kind of survived with fellowships. I had to actually I filed patents, and then I sold the patents to a company. I got money in return to survive, to go to meetings, and so on. It was really a very difficult time, and I was just about to drop out of science. It was maybe I would have dropped out of science if not in 1996. A professor or a director at the Max Planck Institute of Biophysical Chemistry, that's what it was called, in Göttingen. It's a big Max Planck Institute, where I'm now, actually. They became aware of me and said, why don't you come here and apply, and maybe if we give you a chance to try it out. And so I came there to the Max Planck Institute, and then I set up a lab. The truth is that I didn't get enough money to do the experiment. So when I started, I applied for money to the German Ministry of Research, and they called in experts, 12 experts, and they all said, no, it's not going to work. And then the person of the ministry, so the officer, said, maybe these guys are wrong. If you prove that these guys are wrong, you still get the money, and I'm going to dismiss the reviewers. And then I really wrote a letter why these reviewers are wrong, and then the officer decided to give me the money, although the 12 reviewers said this is not going to work. And so the very courageous officer. And then I got the money, and it turned out to work. And so this is before and after. So this is before and this is after. And then it turned out that the resolution is there. And these are so-called nuclear pore complexes. If you zoom in, you see this 8-fold symmetry here. And if you compare it with standard resolution, you can forget it. There's a big difference, of course, between the two. Now, this picture is found in textbooks in the German-speaking world, in Switzerland, Austria, Germany. School kids have this picture in their textbooks. Now, so it turned out to be true. And of course, then people became aware of all this. And then so the idea actually moved to America. So before that, it's very interesting. No one really worked on increasing the resolution of light microscopy with a lens, so with focused light. So this development really came out of Europe, and then so Americans became aware of it. So the idea people became acquainted. Oh, this could work. And there was a guy there, Eric Betzig, 2006. He came up with a similar idea, similar in a sense that it also used on-off for separation. He actually wrote an email to me in 2005 saying, "I'm coming to this field because of your work," and he looked into what I may have missed out, and indeed I missed out the option that you can also turn on and off on a single molecule level. So here in STED microscopy, we turn the molecules off with a donut beam, but you can also turn molecules on and off by, say, a photochemical reaction on a single molecule level. I didn't miss out the photochemical reaction. That I also realized that it's possible. But on a single molecule level, I didn't do because I felt it's too noisy. But anyway, he did it first and demonstrated that it worked. And so I had the honor of sharing the Nobel Prize with him. This is Eric Betzig, and this gentleman, W. Murner, was the first to identify individual molecules with light. And so this STED microscopy and also Palm Storm are two canonical, if you will, super resolution microscopes. I would like to mention that in the prize was given in 2014, but I founded with my former students a company. So this is just to show you that if you make a discovery that is really important and other people want to take advantage of it, then it has a commercial value. And so I founded a company with the patents that were licensed out from Max Planck Institute, because everything I invent belongs to the Max Planck Institute, because I work for the Max Planck Institute, I'm getting paid, I'm getting salary for them. But they gave a license to my former students, and they set up a company with myself. But we didn't take venture capital, no loans or debts, and since then we still have growth. And the company produces actually small microscopes that can be attached to any microscope or bigger microscopes, so a whole array of many versions. So it has become commercially available, this methodology, but since I'm a scientist, I was still driven by science, and I knew that in principle it should be possible to get down to a spatial resolution of 1 nanometer, but none of these methods could do that at the time. At the time, both STED microscopy and also the version first done by Eric Betzig couldn't get better to 20 nanometers. So the practice resolution was not better than 20 nanometers. And I wanted to go down to resolution that is down to the size of a molecule. Now, I figured out, actually just a couple of years before the prize was given, but it was secret at the time, I had just had a patent on it, that if you combine actually the strengths of both that with that of the single molecule method, then the resolution would be even better. And so I introduced a method called MinFlux, which uses single molecules like here, but uses this donut beam, this holy beam, the beam with the hole here for, in this case, excitation. And then you can get very, very high spatial resolution. I'm not going to explain the details, but the truth is that the resolution, say, of these nuclear pores, this is the same structure as before, got even better. These are individual dots that can be associated with individual fluorescent molecules. So these are individual molecules. And you see the resolution is down basically at the size of the molecules, molecular scales here. And if you compare it with the method that won the Nobel Prize, it's here 10 times better than the method that got the Nobel Prize. And if you compare it with the standard resolution, this is 10 times better. And here, the newest version, MinFlux, is 100 times better. So we are now 100 times better than what people thought that the end would be. And this has also become commercially available. So this is also now available for everyone. And many systems have been sold, especially in America. Cutting edge lab in America use these microscopes, also in Europe. So this method is rapidly growing, become very popular. I think there's more than 40 systems around the world by now. And it's really, really exciting technology. It's exciting also, not only because you get a high spatial resolution, because it has a feature that is quite unique. It can detect the movement of molecules with the highest possible spatial resolution. And one molecular movement that is very important in physiology and has been seen was this movement of this protein called kinesin that transports neurotransmitters on microtubules. And you can see it either 10 times more precise or 100 times faster. And I think many interesting discoveries on how proteins work will be made with this technology. And I'm really looking forward to that. I think it's a game changer in the field of biophysics and understanding protein action. And so here you see these tiny steps of this kinesin, how they were actually measured actually with high precision, and you see small steps of 4 nanometers or so. Okay, coming towards the end, I don't want to generate the impression that I was the only one working on it. Of course, I had over the years many people working with me. So this is a collection of the collaborators, the last students of the last 25 years. They have all contributed to this vision, to this idea of getting down to the molecular scale resolution. I'm very proud of them. Many have become professors and are very successful entrepreneurs. That's something that I'm also very proud of. Actually, the company has grown so much, by the way, that there is more than 120 employees. And we're still not sold out to anyone, and we're not going to do that. So zero venture capital, zero debt, still organic growth, and still the same owners. And the city of Göttingen, where the company has its headquarters, actually built a building just for the company. You see also this logo on the side. Whenever you visit Göttingen or Germany, you should come by. So with that, I'm kind of concluding. So as a wrap-up message, what I have learned is that consensus not necessarily equates reality. So of course, there's often consensus on something. Yeah, it doesn't mean it's truth. In fact, if many people say that, doesn't mean it's true. And I think you will understand that, and you will buy to that. So what I'm saying is, you should be suspicious if consensus is too strong. Okay, and then you should think, is this really true, or is something else going on? Then the other lecture or the other message that I would like to convey: the challenging consensus is not always welcome. So if you challenge consensus, like I did, say there's a way to get a better resolution, many people didn't like it. So they said, "Oh, I'm exaggerating. I'm hyping. I just want to create stir. I just want to do a show." Some people said I'm doing just shows or whatever. And this kind of nonsense, So if you challenge consensus, you should be aware of the fact that you're putting many people out of business. Yeah, you're taking away their jobs or their say scientific profile or whatever, and so they won't like it. So don't expect the world to clap hands if you have a great idea. That won't happen. And then the final thing that I'm saying, that if curiosity is actually a good driver for being in science, yeah, very good driver. So you shouldn't do it because you want to help, I don't know what. Yeah, that could be a motivation, but curiosity is a very good motivation. Curiosity very often leads to unexpected breakthroughs. Curiosity, of course, favors the prepared mind, so that's also clear. But if it's a breakthrough, it always means economic value. That's a law. I'm convinced about that. If it's not leading to economic value, it's not a breakthrough. it may not lead immediately to economic value, but in the end, it has always economic value. And if you're lucky, you may also win a share or of a Nobel Prize. So thank you very much for listening.
Okay, thank you very much, Stefan. So then our session is open for discussion questions. Okay, so anything you have in mind, please. You have a microphone? Yes, 2 microphones here. Please go and ask questions.
Thank you for lecture. I'm interested in observing to make or break the bonding of small molecules in chemical reactions. So can your work allow us to do it? So do you understand?
Yeah, So your question is whether I can observe or small bonds in chemical reaction.
Yes.
The answer is no, because not directly, at least, not trivially, because what we observe in fluorescence microscopy is fluorescent molecules. We do not observe the molecules or the proteins themselves. We see just fluorescent molecules. If you look into reactions of fluorescent molecules or something, then it may work, yeah. But it has to be a fluorescent molecule. That is important. If it's just a general, say, molecule, chemical molecule, then you won't see directly. And of course, in biomolecule, it works because biomolecules are rather large, and you can relatively easily attach a fluorescent molecule to them, and then you can see conformational changes of that protein, for example, or enzyme.
Okay, thank you.
Okay, any other question? Okay, yeah, just stand. Please say your name also.
This is Çiğdem Kamburoğlu from Turkey. When we struck something in our research, they usually say that you need to change your point of view, but through your story that you change a country, and then how did it affect you, and do you suggest that we sometimes change where we live when we struck something, or how did it help you?
Yeah, it's there's I often get questions concerning whether I can give a personal advice. This is really hard because so I lived my life in my own way, and everyone has to do it in his or her own way. This is really really important, and so taking advice is something that is probably not always good. I'm just saying that. Did it help me to stick with my idea? Yes, in retrospect, yes. But of course, many people have ideas and they stick to it and they fail. I think what's very important is that you have high aims in that sense. If in science, it's always good, especially if you're young, to work on an important problem, not an unimportant problem. To work on an important problem that kind of looks improbable or difficult, but at the same time be realistic about potential outcomes and failure. So of course, the problem that I worked on was very difficult and considered unsolvable. But I had a very realistic, say, assessment of the chances that it would work. So I assessed what could go wrong, yeah, and what could work. And so I had a better, say better view about the reality than my competitors. So that's why I succeeded. It's not because I was just brave or so, but I had a better my view was more realistic than of the competitors. I figured out what would be the problem and what could work. And I identify the problems and I identify the potential in a correct way. And going abroad, does it help? Yes, it can help, especially if if you're in a foreign country, then you can more easily concentrate on science, because there's no other distraction, and that can help. On the other hand, of course, if the country is very different, you may face other difficulties and distractions because of the difficulties that you're facing. So there's no general rule. There's no general rule.
Thank you.
Okay, next question. Yeah, please.
Hi, this is Mong Lan from Singapore. I'm working on biology medical fields. So my question is, you are from a physics background, but your discovery is actually very beneficial for biologists like me. So my question is, what's your take on such transition from a physics PhD to looking at some biological questions, and how do you think we can foster type of interdisciplinary collaborations to, help each other?
Yeah. So I think physicists have, in modern biology, have made enormous contributions. If you look back already, even in the 30s, 40s, 50s, of course, I think the invention of X-ray, crystallography, DNA, of course, and wouldn't have been discovered, or the structure of DNA, without physicists. Many, of course, especially structural biology, has enormously benefited from physics. Still, I think physicists can make huge contributions to biology, especially molecular biology. As I said, now the method that I showed towards the end, MinFlux, has the capability of seeing protein movements with 1 nanometer per millisecond spatial temporal resolution. This is unheard of. This was 5 years back impossible. Impossible. So this is 100 times faster than what people have done so far. And I can tell you, results are just pouring, because you apply to kinesin, or you can apply to, I don't know, dynein or whatever, these molecular motors, and you will see things that no one has seen before. You can sort out problems that were there lingering around for 40 years. And now, because the methodological demand is so huge, they will be solved. And if I were a young physicist, biophysicist, I would go into this field, because there is a new methodology that has huge potential, and the limits of that methodology are not reached. So I'm saying 100 times faster. It could eventually become 1,000 times faster. And then imagine what you can see with that. So yes, I believe physics is still making big contributions to biology, and will make big contributions in the near future as well. How do we foster collaborations? In my view, you see, I never studied biology. I didn't do any lectures in biology. As a school kid in 10th grade, I gave it up. And so what I did is I actually mingled with biologists, had coffee, with biologists, and I asked them silly questions, believe me, very silly questions, because I didn't know biology. And they would explain it to me. And over the years, of course, you get a really good understanding, because you ask silly questions, you get interesting answers, simple answers, because people realize that you were dumb in biology, and then they explain things very clearly. And so, and every now and then I look into books, of course, but interaction, personal interaction, is a very good way of getting a good training.
Thank you.
Okay, so I have another question.
Hello, Gul from the Weizmann Institute in Israel. So one of the things I find very inspiring about super resolution is that it exposes implicit assumptions in Abbas derivation, which were, at least to me, not evident before I heard about super resolution. And my question is, one, if that was a part of your discovery process to see that there were some assumptions that could be broken? And second, if there's any other barrier in physics that you think is based on some assumptions that are ready to be challenged?
Yeah, so to clarify that the assumption was, and I tell you what the assumption was in Abe's equation, the assumption was that the resolution had to be done by waves. The information had to be just carried through waves. That was in Abe's theory. And that's why with Abe's theory, you couldn't get any further because waves, of course, because of the wavelengths, cannot carry information that is, say, beyond half the wavelengths of light. Yeah, because it's averaged out. And that was Abe's theory. And this is such a compelling idea, yeah, that physicists learn this in second year or first year of physics study. The idea is so nice and so compelling that people felt that's clear that there is no other way of solving the problem. But what I realized that it's silly to ask the light to carry the information. It's better, yeah, to play with molecular states and then make the separation by molecular states, by making them distinct. And if you make them distinct, yeah, by putting them in molecular states, you don't have to ask the light to carry the information. And so my fundamental discovery, if you ask me what is the most important discovery I made in my life, or one of arguably the most important, I fully realized that the way to go is to play with the states in the molecule for separation, and there are states that you can play with. And of course, there was no such thing in Abe's theory because it was all based on waves. And you may know or not know, there was also another methodology that tried to do super resolution with light, optical. It was called near field optics, where they tried to put the light through a tiny fiber. And that also relied on waves. They also, that was, didn't work in the end, not properly, yeah, because it relied on waves. So what I realized is you have to separate by states. And that is a very profound thing. And once you have realized that, then all kind of evolves from there. Of course, there's still a way to go, yeah, because you have to develop, you have to define a concrete way, you have to make it better and so on, that convinces the world. But that was the big thing. That was the big thing. That was clear to me at the time. So that was clear to me in the early 90s. Abe's theory is not wrong, but it had as you said, it had the assumption that the information has to be carried by waves, and that is not true. It not necessarily has to be like that. Okay, and then the second question: are there other laws? Some laws are perhaps perceived, because they're overgeneralized. Like Abe's theory was too overgeneralized, because people fall in love with an idea, with a concept, and then like with Abe's concept, they fall in love with a theory, and then they overgeneralize it. So I'm not excluding there are other theories there as well. Yeah, physical, chemical, biology. I'm sure in biology it's even more. That people are in love with because it's simple, it's appealing, it's nice, but in the end it may be not completely true because it's overgeneralized, because people think too highly of that law. So if you look at, say, different laws from that perspective, that they might be overgeneralized, you may find something that is not entirely general or as general as it seems.
Okay, so any other question? Actually, we have still 20 minutes to go. Yes, and actually we had many questions in advance, and there are many similar questions from students or participants, and so I like to ask those questions to Stefan. And the one question is, it's like, do we need electron microscopy since you have achieved already a molecular level resolution? So So many situations will be optical microscope replaced. But, yeah.
Yeah. So of course, yes, because electron microscopy can see things that fluorescence microscopy or super resolution fluorescence microscopy cannot see. As I said, fluorescence microscopy has the limitation that it doesn't see the proteins themselves. It always sees fluorescent molecules, nothing else. And so in many cases, the fluorescent molecules do not really represent what you actually want to see. And that is the case the closer or the higher the resolution gets. So if the resolution is down to a nanometer or two or so, then you have to be aware of the fact that the fluorescent molecule has its own size, and the fluorescent molecule might be linked to a protein, and there's a linker in between. So the resolution is almost too good. But that's not quite true, because you can still take advantage of that. But having said that, electron microscopy, of course, has made big strides when it comes to seeing structures. It's replacing, to some extent, X-ray structure finding. So there was a Nobel in, I think, 2016 or 17, a couple of years after I got it, on cryo-EM. So electron microscopy is a fantastic technique, but of course it's used for other things. Yeah, but to answer the question, yes, there is many problems out there in biology where you shouldn't use the electron microscope, but the fluorescent microscope. And people, when they thought about in the past about seeing if two proteins are very close together or something, yeah, say 5 nanometers together, they said, oh, you have to use the electron microscope, because if it's 5 nanometers together, you will not see it with light microscope. If you can label it with a fluorescent molecule, then you can see 5 nanometer distance easily by now, even with a commercial system, yeah, or 3 nanometers. As a matter of fact, you can even see distances down to 1 nanometer and below, and even further. So there is many cases where you can basically use the fluorescent microscope, so a super resolution fluorescent microscope, and you don't have to use the electron microscope. Electron microscopy is now being used for other things.
It seems like the physical limit of optical microscope already reached the level of this molecular or atomic level, but the problem is not in physics. It's more like labeling or like chemistry or its application side. So I think we also have to work on very interdisciplinary way to reach the level. So yes, and so then related to that question, some participants are wondering, artificial intelligence or machine learning will help to go further based on your technologies.
Yes, I think so, yes, because machine learning, of course, is very good at recognizing patterns. And of course, many images are kind of patterns or distributions. And if you train your system with certain patterns, it may recognize similar patterns in another sample much more easily than the brain would do. And so I'm convinced that that in the near future, many microscopes, of course, and of course microscopy pictures will be used and say examined with artificial intelligence.
So do you have some more questions? Listening to those discussions, if so, yes, please. Yes, we have time.
Good afternoon. My name is James from Osaka University. So I'm really impressed by the schematic of breaking the diffraction limit, and I'm really curious of one thing. When a short wavelength excites the molecule, which fluoresces it, and then a longer wavelength quenches the spot. So I was thinking, like, when you go to shorter wavelengths, like soft X-ray wavelength, what do you think would happen to the molecule? It's not just fluorescence, but kind of excitation as well.
Yeah, it may work. There might be transitions where it works. I mean, I'm not too much familiar with the transitions that are taking place actually there. But I mean, in the end, it's all about state transitions and make a separation state transitions. And of course, conceptually, at least, it's possible to think about, say higher energy states, of course. And so the quenching is done by stimulated emission, and so it's basically a transition to a lower state. But you have to keep in mind that fluorescent molecules, organic molecules, are very good because the state into which the molecule is quenched is a rapidly decaying state. And that prevents the molecule from being excited by the same beam back and forth, because otherwise you would have a oscillatory transition between the lower state and the high state. That doesn't take place because there is a quick transition to another state in that is lower energy. So basically, you need 3 states to do it. It's not just the excited state and a ground state. So from a physics viewpoint, you need 3 states. So that's a detail that I didn't talk at length here because it's a general audience. But conceptually, if you are an expert in X-rays or so, there might be a way of doing that. Yeah, I'm not excluding that. Conceptually, it can be extended. It's not just about, say, fluorescence. There's X-ray fluorescence, as you know, of course.
So there's a metastable state existing between those ground and excited.
Yeah,
okay.
there's a metastable state in which you pump, yeah, and that metastable state decays quickly, and then that metastable state is always empty. That's why you can pump into it from the top.
Thank you very much.
Okay, any other question? Okay, so let me ask last question for me. And as I said in the introduction, so we are surprised of the Nobel Prize in chemistry. So I think you're also surprised that the chemistry prize is given to the microscope development. So could you share your thoughts and also your understanding why?
Yeah, if you look back in 2014, you may remember that Nobel Prize in Physics was actually given to the blue LED, yeah, to 3 Japanese scientists, and actually when on the first day before the Nobel lectures were given, the head of the Academy of Sciences, both of the physics and the chemistry section, said, okay, was the physics prize a chemistry prize or was the chemistry prize a physics prize? Because, the blue LED, which was invented in Japan, it was done in a chemical company, to a large extent. Mm-hmm. And so that could have been also a chemistry prize because it had many chemical challenges, and just like our prize could have been a physics prize because it solved a physics problem. But in the end, the committees decided that the blue LED is a physics prize because it's light, and this is a chemistry prize because it's applying to biomolecules. That was the argument. It's biochemistry in the end. It's applied to biochemistry, but as said, it's physical chemistry. It's not real chemistry in that sense. It's physical chemistry. Yeah. But the blue LED was also physical chemistry, let's face it.
Yeah, the company name has the chemistry in the company name, right? So.
Yeah, sure.
Okay, thank you very much. So I think the students or participants have more questions, and we also have time for discussion session later. So please also ask any question you mind. It's a small room. You can feel free ask any question there. So, but I'd like to close the session at this moment, and I'd like to thank Stefan again for your great lecture and sharing us a lot of thoughts. Thank you.
Thank you very much, Dr. Hell and Dr. Fujita. Let us show our appreciation with a round of applause.